Are your brains full of action potential stuff? Stress Kitten says yes. Stress Kitten says no more, please. But let's do yet more details about action potentials. It won't be bad, I promise. All right, some more details. So what starts this whole thing? We know we got to get up to threshold, but what initiates an action potential? And it's going to be anything that causes sodium ions to begin to move inward, not through the voltage gated channels, because you have to hit threshold to have them move in through voltage gated channels, but other things can make more sodium ions move in. So it might be chemicals, different neurotransmitters, and we'll talk about those in the next video. A mechanical stimulation can actually bend and open up a channel so calcium or sodium can come on in through a mechanical signal. Electrical stimulation, a number of things can make sodium come on in. And then what happens is this is going to open up some sodium channels, and then sodium rushes in and depolarizes it. And then when you hit threshold, that opens up the voltage-gated sodium channels. I will just say local anesthetics like Novocaine or lidocaine, what these do is they prevent sodium channels opening in response to depolarization. So they prevent action potentials on pain pathways. So no pain is going to go to the brain. All right, now where are the action potentials initiated? They are initiated at the axon hillock. That is where the soma meets the axon. And that's where you have the most voltage-gated sodium channels. Remember, we also have a lot in the nose of Ranvier. And the signals are going to come, you get a signal going to the dendrites, and those are going to move to the soma, and then they're going to arrive from the soma to the axon hillock. And if there's enough of them, then enough of what we call EPSPs, excitatory postsynaptic potentials. If you take neuroscience with me, we'll talk about those. But they're tiny little bits of depolarization. So every time a neurotransmitter binds to a dendrite, for instance, it might cause a 0.5 millivolt depolarization. 0.5 isn't enough. We need a 15 millivolt depolarization because we have to get from -70 to -55, that's 15 millivolts difference. So one tiny little graded potential is what we call them isn't enough. You have to have enough signal. You have enough neurotransmitters from the different neurons saying, yes, fire, 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 fire. And if enough of them add up together, that may send a signal big enough to the axon hillock to open up the voltage-gated channels. Now we've talked about threshold. What is threshold? Threshold is when you hit the voltage, whatever that voltage is necessary to open up voltage-gated channels. In this case, it's -55. And once you hit -55, whoosh, you don't have to open up a little one here and a little one here. They open up themselves. The voltage-gated channels open up. You don't have to get the signal another way. Another thing, we say that action potentials are all or none. What we mean by that is you don't have a small action potential or a large action potential. All right, they all look the same way that I've drawn them. They always look like that. And what that means is if you have a depolarization of less than 15 millivolts, you're not getting an action potential. It's not like you get a little action potential. So if you're at -70 and you only get up to -65, a 5 millivolt depolarization, yeah, you didn't hit threshold. You don't get an action potential. But let's say we have a lot of signals. We get from -70 up to -45. You don't get a bigger action potential. Hitting voltage, that's all it is. So depolarizations of less, you don't get an action potential. Depolarizations of more that get you above -55, you get the same action potential. I could think of it like squeezing a trigger. If you don't squeeze the trigger hard enough, the bullet's not coming out. It's not like it just falls out slowly and plops on the ground if you didn't squeeze hard enough. But if you squeeze the trigger really hard, the bullet doesn't come out any faster or go farther. It is or it isn't. It's all or none. So you hit -55, it's a depolarization of 15 millivolts. You hit that, you got an action potential, always the same size. But what that also means is that a single action potential doesn't give you degrees of information. What that means is, how do I know if it's a loud sound or a quiet sound? Or if I'm tickling you, if I'm punching you? It's not that you get a bigger action potential with a louder sound. You have more action potentials, or more that come close together, or more from a single area of your skin where I'm pushing harder rather than pushing lightly. So one single action potential doesn't give degrees of information, doesn't say it's louder, or it's stronger, it's lighter, it's weaker, whatever. You need more action potentials or more closer together. In neuroscience, we talk about that more. But an action potential just says, yes, a signal on this nerve. All right, a few more terms. A refractory period. What is a refractory period? It's if you have a second stimulus, whatever caused your first action potential is a stimulus, so a second one will not produce an action potential because you're busy firing. You're already doing your thing. You can't have another one on top of it if it's an absolute refractory period. So, and I'll illustrate this in just a second. An absolute refractory period is you just had a stimulus that's leading to an action potential. If you have another stimulus right away, they don't build on each other. It's not like muscle twitches. Muscle twitches summate. Remember temporal summation? They build on each other till you hit tetanus. That doesn't happen with action potentials. If you have one action potential is firing, you have another stimulus, it's firing. It's not going to produce another one. So you cannot make another action potential no matter what. That's the absolute refractory period. During the relative refractory period, yeah, if you have a big enough depolarization, you can get an action potential. So this is better if I illustrate it. Here's always our action potential. Here in green is our stimulus. Our stimulus happened and that allowed somehow sodium to leak on in. And so this guy's firing an action potential. If we have another stimulus here or another stimulus here, you can't fire another one on top of it. It's already doing its thing. All right, your sodium channels have already been inactivated and the potassium channels are already open. You can't generate a new action potential until you get down to minus 55 again. So when it goes from minus 55 up to plus 35 and then minus 55 again, you can't. There it is. This is the absolute refractory period till you hit here. So I don't care how many stimuli you have. Nope, you're not firing another one. And I also teach human sexuality. Men have a refractory period. Excuse me, but women can have multiple orgasms. You're firing one, you can fire another one. Men can't do that. And we literally call it the refractory period because you're firing one. You're busy, you're firing it. You can't fire a second one while you're firing one already. So just maybe give that a little bit of context to hope that helped. All right, now the relative refractory period is when it gets back down to minus 55 until it again gets up to minus 70. Here, you can fire another action potential if it's strong enough, if the stimulus is strong enough. So here's our original stimuli. Hooray, it got us an action potential. Any stimuli here, nope, we can't fire it. But once we get that back down to minus 55, if we have another stimulus and it's strong enough to get us to minus 55, yep, we can fire another one right there. So if the other stimulus is hitting while we're in hyperpolarized, if we're at minus 90, it has to be a bigger stimulus to get us up to minus 55. Enough to get to threshold, then that's the relative refractory period. Yes, you can fire another action potential from minus 55 until you get back to minus 70. A few more things. Unidirectional flow. Action potentials only go in one direction. They only go from the cell body down to the axon terminal. They can't go backwards. And they go from node to node. They hop from node to node, and that's called saltatory conduction. And you generate a new action potential at each one. Oh, I don't think that's in your notes. Saltatory conduction, you should put that in if you haven't already. But that is, you generate a new action potential at each node. It hops from node to node. You don't generate a new one at every teeny bit of the membrane. And with that, it can only go in one direction. It can only go from the axon hillock down towards the axon terminal. It can't go backwards. First of all, there's no point because what you want to do is get to the axon terminal and spit out the neurotransmitter. There's no point in going backwards. But technically, you can't go backwards because the patch of membrane you just left is in its refractory period. It's just fired an action potential. You can't fire another one. So if that signal were to go backwards, maybe it does. The sodium ions do go backwards, but the patch of membrane that you just left, so here you fired one here, there's sodium ions around here. Some of the sodium ions are going backwards, but this guy, this patch of membrane here, is in its refractory period. You can't fire another one. It can only go in one direction. And the last few things to close this out is how fast does the signal travel down the axon? Two factors determine how fast it goes. The diameter, the wider the diameter, the larger diameter is faster conduction. All right, so if you have a fire hose, things go faster than if through a drinking straw, right? Especially if the straw is leaky. And so we're going to see that the neurons in our body that you need faster transmission tend to be wider. They have a larger diameter. Motor neurons that tell your muscles to react quickly, they're large diameter. The other thing is myelin. And again, neurons that you need a fast signal from, they're myelinated. So myelin helps prevent the flow leaking across that membrane. You don't want your sodium ions just leaking everywhere. You want them where the voltage gated channels are. I'm going to skip this whole thing about the hose. You don't need the analogy. But basically, where your voltage-gated sodium channels are, they're at the nodes of Ranvier. They have a lot of voltage-gated channels, and the signal is going to hop from node to node to node, from the axon hillock down to the axon terminal. Okie dokie. In our next video, we will talk about neurotransmission and neurotransmitters. And we're good.